Every whole number you can name is built from prime numbers in exactly one way, and yet no one on Earth can tell you where the next prime will fall. As the numbers grow larger, prime numbers slowly drift farther apart. There is a beautiful formula that predicts how quickly this happens, and most of the time it is astonishingly accurate, but never perfect. Every stretch of numbers contains a small difference between prediction and reality, and understanding those tiny differences has become one of the deepest unsolved questions in mathematics. Tonight, we follow that error, from a teenager scribbling in logarithm tables, to 8 pages written in Berlin, to a line on a map where the answer either lives or does not. And if at some point tonight you find something worth carrying into sleep, a little wonder, a little quiet, a like or a subscribe would mean a great deal to me. Not for any algorithm, just so I know you were there. Now, let us begin. Take any number you can name. 60. It breaks apart into 2 times 2 times 3 times 5, and there is no second way to do it. You cannot assemble 60 from any other set of prime building blocks. Try 84, or 6012, or a number so large it would fill this room if you wrote it out, and the same thing holds. One recipe, one set of primes, no alternatives, no exceptions, no number anywhere on the endless line that can be built 2 different ways from the primes. This is why mathematicians reach for the word atom when they talk about primes, and the comparison is more exact than it first sounds. A prime is a whole number greater than 1 that cannot be split into a product of smaller whole numbers. 2, 3, 5, 7, 11, 13. Each one is indivisible in that specific sense. And just as every molecule of water is 2 hydrogen atoms bound to 1 oxygen atom and never some other arrangement, every whole number is a unique cluster of these arithmetic atoms. Chemistry has its periodic table, a finite chart of elements you could pin to a wall. Arithmetic has the primes. The difference, the one that will bother us for the next several hours, is that nobody has ever pinned the primes to a wall, because nobody knows where they all are. You might expect there to be a last one. Most patterns in the physical world run out eventually. The elements stop somewhere past the 90th or so before the nuclei grow too unstable to hold together. Coastlines end. Even the number of atoms in the observable universe, enormous as it is a specific finite count. So it would be reasonable to guess that the primes thin out and then simply stop, that somewhere out there sits a final, largest prime, and past it every number can be broken down further. That guess is wrong, and a man in Alexandria showed exactly why more than 2,000 years ago. Here is how the reasoning runs. Suppose someone hands you a complete list of every prime that exists. Any list, as long as it claims to be all of them. Now, multiply every prime on that list together into one gigantic number, and then add one. Call the result the new number. That new number, when you divide it by any prime on the original list, always leaves a remainder of 1, every single time, because the product of all those primes was, by construction, evenly divisible by each of them, so the next number up, 1 greater, cannot be. Which forces a conclusion the list maker cannot escape. Either the new number is itself prime, in which case it is a prime that was not on the supposedly complete list, or it is not prime, in which case it must be built from primes, and none of those primes can be on the list either, because everything on the list leaves that stubborn remainder of 1. Either way, a prime exists that the list left out. And this works against any list you are ever handed, no matter how long. There is no complete list. The primes never end. I want to slow down on one thing. The new number, the product plus 1, is not necessarily prime itself. People remember it that way, And it is not true. 2 times, 3 times, 5 times, 7 times, 11 times 13, plus 1 comes out to 30,031, and that number is not prime at all. It factors into 59 times 509. But notice what happened. 59 and 509 are both primes, and neither of them was on our starting list of the first 6. The argument never promised to hand us a new prime directly. It only promised that a new prime is hiding in there somewhere, forced into existence by that remainder of 1. The proof does not build the next prime. It proves the next prime has nowhere to not exist. There is also a small historical correction hiding in the way this proof usually gets told, and it matters for how we think about the whole problem. The argument is almost always described as starting from a lie, from the assumption that the list is complete, and then blowing that lie up. A proof by contradiction. But that is not quite what the original does. The original reasoning never needs the list to be complete. Hand it any finite collection of primes at all. No claim of completeness required. And it manufactures one more that is not among them. It is a machine for producing new primes on demand, not a trap for catching a false assumption. That distinction sounds like pedantry until you feel its weight. It means we have known, with total certainty, for over 2,000 years, that this sequence runs forever. We possess a flawless proof that the primes are infinite. And in all that time, with all that certainty about their number, we have never gained the matching certainty about their arrangement. Because knowing a thing is endless tells you nothing about where its pieces fall. The even numbers are endless too, and their arrangement is trivial. Every other number, forever, no surprises. The primes are endless in a completely different spirit. We have the proof that they go on, printed in every textbook, unshaken for 2 millennia, and we still cannot look at a number with 100 digits and say whether it is one of them without grinding through an actual test. We have infinite supply and zero address book. An unbroken chain of certainty about how many, sitting right beside a total blank about where. So the primes are the atoms of arithmetic, indivisible, unique in how they combine, guaranteed to never run out. We have all of that nailed down. What we do not have is the one thing you would most want from a set of building blocks that constructs every number in existence. If they truly are a periodic table, then where are the rows? Where are the columns? What is the shape of the chart nobody has ever managed to draw? Write out the numbers from 1 to 100 and circle the primes, and the first thing you notice is that they refuse to keep a rhythm. 2 and 3 sit right next to each other, then a gap to 5, another to 7, and already the spacing has changed twice. 11 and 13 come as a close pair. So do 17 and 19, but then 23 stands alone, and after it you have to walk all the way to 29 before the next one appears. Up close, the primes look less like a pattern and more like a coastline drawn by someone who kept changing their mind. The pairs are the part that pulls at you first. 11 and 13, 17 and 19, 29 and 31. 2 primes separated by a single even number, as close as 2 primes can possibly be, since apart from 2 and 3 themselves, no primes can sit directly side by side. These are the twin primes, and they keep showing up no matter how far out you count. 101 and 103, 10,109, and its twin 2 above it. People have found twin pairs with tens of thousands of digits. And here is the thing nobody can prove. We do not know whether the twins go on forever. We know the primes are infinite. That was settled 2,000 years ago. But whether these tight little pairs keep appearing all the way out, or whether at some unimaginable height the last twin pair occurs and there is never another, is a question that remains completely open right now. The pairs feel like a rule. We cannot show they are one. Now push the other direction, away from the clusters, into the empty stretches. These are called prime gaps, the runs of consecutive numbers where nothing prime appears, and they raise the opposite worry. If the primes can bunch up into twins, can they also spread apart without limit? Could there be a stretch of 100 numbers in a row with no prime? 1,000? 1,000,000? The answer is yes, and what makes it unsettling is how simple it is to prove. You do not have to go hunting for these deserts and hope you stumble on one. You can build them to order, any size you like. Suppose you want a run of 6 consecutive numbers with no prime in it. Take the number you get by multiplying 1 times 2 times 3 times 4 times 5 times 6 times 7. That product is 5,040. Now look at the 6 numbers just above it. 5,042 is even, so it is divisible by 2 and cannot be prime. 5,043 divides evenly by 3, because the base number already contained a 3. 5,044 is divisible by 4, 45 by 5, 46 by 6, 47 by 7. 6 numbers in a row, each one forced to be composite, each one carrying a specific small divisor baked in on purpose. And nothing about this trick stops at 6. Want a gap of 1,000? Multiply up through 1,001 first, then walk the numbers above it. Want a gap the size of the galaxy's atom count? Same recipe, just start higher. There are prime deserts of every length, out there waiting, as long as you are willing to climb high enough to reach them. So the primes cluster into twins that may or may not be infinite, and they scatter into deserts that provably have no ceiling, and both of these things are true of the same sequence at once. Sit with attention there for a moment. The pairs pull the primes together as tightly as arithmetic allows. The gaps fling them apart with no bound whatsoever. A well-behaved pattern does not do both. A grid does not do both. And yet the primes do, forever. And there is no height you can climb to where they finally settle into one behavior or the other. You might reasonably hope that this is just a problem of not looking closely enough. That the local rule is there, and we simply have not been clever enough to spot it. Physicists faced things that looked random and eventually found the machinery underneath, the hidden gears that made the chaos deterministic. Maybe the primes are the same. Maybe there is a formula, some expression you feed a number into, and out comes the next prime, and the whole apparent mess resolves into order the moment you find the right key. People have searched for that key for centuries, not casually. Some of the sharpest minds in the history of the subject went looking for a formula that generates the primes, one after another, in sequence. Nothing has ever worked. There are formulas that produce a lot of primes for a while and then fail. There is a famous one, a simple square and add expression that spits out prime after prime for its first 40 inputs and then breaks. There are formulas that technically generate only primes but are useless, because to run them you already have to know the primes going in, so they tell you nothing you did not start with. What has never been found, and what many now suspect cannot exist in any useful form, is a genuine rule that looks at where you are on the number line and tells you where the next prime lands without simply testing every candidate one at a time. The local view gives us nothing. Standing at any single prime and looking at its neighbors tells you almost nothing about the next one. The gaps do not follow a countable beat. The twins do not arrive on schedule. Every attempt to predict the next prime from the last one dissolves. Where is the next prime? Where does this pattern come from? Standing among the numbers, magnifying glass in hand, examining them one at a time, we get chaos with no visible source. 2,000 years of certainty that they are infinite, and up this close, not one reliable clue about their arrangement. But there is another way to look at anything that seems random when you are standing inside it. You can step back, you can stop asking where the next one is, and start asking a question that sounds like surrender, but turns out to be the opening move, not where is the next prime. How many primes are there? Below any number you choose. Stop chasing the individual primes for a moment and do something that sounds almost too plain to be worth the effort. Just count them. Pick a number, say 100, and ask how many primes came before it. 25. Below 1,000? 168. Below 10,000? 1,229. Below 1,000,000? 78,498. You have quietly stopped asking where any particular prime sits. You are asking how crowded the primes are up to a given point, and that shift from location to population is the hinge the entire subject turns on. Give the count a name so we can hold on to it. Mathematicians write it as pi of x, though it has nothing to do with circles. It just means the number of primes up to whatever you feed in for x. Draw its graph and you get a staircase, flat. Then a jump up by 1 exactly when it clears a prime, flat again, another jump. Down at the bottom, the steps come fast and tight because the small primes crowd together. 2, 3, 5, 7, all elbowing into the first short stretch. Climb higher and the steps stretch out. The staircase never stops rising, but the landings between jumps grow longer and longer the further up you go. The shape of that widening is the first true regularity anyone ever pulled out of the primes, and the person who pulled it out was 15. In the early 1790s, a teenage Carl Friedrich Gauss came into a set of logarithm tables that happened to ship with a table of primes tucked in beside them. Most people would have used the logarithms and ignored the primes. Gauss did the opposite. He started counting them in blocks of 1,000, tallying how many fell in the first 1,000, the second, the third, filling page after page by hand, treating the whole thing as a private pastime he would return to for the rest of his life. Block to block, the count jittered, never steady, never flat. But underneath the jitter he caught an average, a rate of thinning he could state exactly, and he wrote it down. He did not publish it. He mentioned it to almost no one. And only decades later, an old man by then, described it in a letter to the astronomer Encke, recalling the boy who had counted primes in the year 1792. The rate itself is the seed of everything ahead. Around any number, the fraction of nearby numbers that turn out to be prime falls off in lockstep with that number's logarithm. Near 100, roughly 1 number in 5 is prime. Near 1,000,000, only about 1 in 14. Near a 50-digit number, you might test more than 100 candidates before you land on a single prime. The density does not crash to zero all at once, and it does not hold level. It fades, gently, on a schedule set entirely by how high you have climbed. Gauss's whole discovery is that the thinning has a law, and the law is the logarithm. Now, why the logarithm, of all things? That is not a number to fall out of a pile of primes, and it is worth understanding why it shows up rather than treating it as a magic word. Think about what has to be true for some large number to be prime. It cannot be divisible by 2, or 3, or 5, or by any smaller prime at all. The bigger the number, the longer the list of smaller primes that each get a chance to divide it and knock it out of the running. As you climb, more and more potential divisors pile up beneath you, and each one thins the field of survivors a little further. When you work through how those chances stack, one prime's filtering on top of the next, the surviving density comes out proportional to 1 over the logarithm. The logarithm is what you get when a quantity is worn down by a growing crowd of independent factors, each taking its cut. It is the natural signature of exactly this kind of repeated compounding thinning, so its appearance here is not a coincidence to marvel at. It is the fingerprint of the sieving the primes do to each other as they climb. Gauss was not entirely alone in this. Around the same years, the French mathematician Adrien-Marie Legendre arrived at a very similar law from his own tables and, unlike Gauss, actually published it, complete with a fudge factor, an extra little constant he tuned to make the fit look better for the numbers he could reach. For a while, Legendre's tweaked version seemed sharper. It hugged the known data more tightly. But that constant was the tell of someone fitting a curve to the numbers in front of him rather than uncovering the law underneath. Push far enough out, and the fudge factor drifted wrong, and Gauss's plainer, unadorned version, the one with no tuning at all, held up better. That is the first quiet warning this subject gives you, and it will come back to haunt us near the end. A formula can match every number you have ever checked and still be telling you a lie about the numbers you have not reached yet. Gauss did one more thing with his density. If you know how thick the primes are at every altitude, you can add up all that thickness from the ground to any height and turn a local rate into a total count. You sum the density across the entire climb. That running sum has a name, the logarithmic integral. And for now, the machinery under it matters less than what it produces. It takes the local observation, primes thin like the logarithm, and folds it into a single smooth curve that tries to trace the ragged prime staircase all the way up. A curve laid over the steps, riding their average, blind to every individual jump. When you finally draw that smooth curve on top of the real staircase, the agreement is almost unfair. The steps jump and stall and jump again, ragged as they ever were, and the curve threads straight through the middle of them, climbing at exactly the rate the steps climb on average. Low down, you can spot a little daylight between them here and there. Push out to larger X, and the two lock together so completely that on any ordinary graph your eye cannot separate them. It looks, for all the world, like the chaos has been caught. Like one clean curve has swallowed the primes whole and there is nothing left to explain. Except a curve that hugs the data is not a curve that has been proven, and Gauss knew the difference better than anyone. What he had was a conjecture, a pattern seen in a mountain of hand-counted evidence, and Legendre's drifting fudge factor was fresh proof that patterns seen in evidence can betray you the moment you climb past where you looked. The primes obeyed the density law for every case anyone on Earth could check. That is a different thing from knowing they must obey it forever, all the way to infinity, with no point far out where the beautiful agreement quietly comes apart. Turning that lucky fit into an ironclad law would take another full century, and it would force mathematics off the number line entirely onto ground Gauss himself never walked. So here is the sharp edge we are left holding. The curve tracks the staircase perfectly, for as far as any human has ever counted. How could anyone ever prove it keeps doing that, step after step, with no end, forever? For 100 years, the smartest thing anyone could say about Gauss's curve was that it was probably right. Not proven, probably. The primes tracked it for every number people could reach, and that was the entire case. A mountain of agreement and no bedrock underneath it. Turning that probably into a certainty is the story of this chapter, and the strange part is where the certainty finally came from. It did not come from studying the primes more closely. It came from leaving them behind. The precise statement is called the Prime Number Theorem, and it says this: take the count of primes up to some number, and take Gauss's smooth estimate for that same number. As you push the number higher and higher, the ratio between the true count and the estimate closes in on exactly 1. Not that the two are ever perfectly equal at any finite point. They are not. It says the gap between them, measured against the sheer size of the numbers involved, shrinks to nothing in the limit. The estimate becomes proportionally flawless, even if it is never flawless outright. There is a subtlety folded into that word estimate, and it decides which curve you use. Gauss actually offered two versions of his guess. The simpler one just divides your number by its logarithm, a rough proxy for the count. The sharper one is the running sum we built at the end of the last chapter, adding up the prime density across the whole climb. Both versions obey the prime number theorem. Both have that ratio close on 1, but the running sum, the logarithmic integral, tracks the actual staircase far more tightly at any given height, and the reason is almost obvious once you see it. The plane division uses the prime density at your final altitude and pretends it held the whole way up. The running sum honors the fact that the primes were thicker lower down and adds up the real density at every level of the climb. One takes a single snapshot and stretches it. The other integrates the truth at each step. The second is bound to fit better, and it does. So the target is clear. Prove that ratio closes on 1 forever, for the running sum, with no escape. The trouble is that everything we have said about the primes so far lives on the number line, and the number line gave us nothing but chaos up close. Counting helped. Counting revealed the smooth density. But counting alone, staying among the integers, was not enough to prove the density law never fails. The first real progress came from Pafnuty Chebyshev, working in Russia in the middle of the 19th century. He managed to prove that the ratio, if it settled anywhere at all, had to settle near 1. More precisely, he pinned it into a narrow band, never straying more than about 10% from the target in either direction, for all large enough numbers. That was a genuine victory. It meant Gauss could not be badly wrong. But Chebyshev could not close the band to a single point. He could trap the answer in a corridor and never force it to the exact value 1. Something was blocking the final step, and no amount of cleverness on the number line could get past it. The block was cleared 30-odd years later, in 1896, and it was cleared twice, in the same year, by two men who had never coordinated. Jacques Hadamard in France and Charles-Jean de la Vallée-Poussin in Belgium each proved the prime number theorem independently, arriving at the summit by their own routes within months of one another. After a century of probably, the certainty landed from two directions at once, and that coincidence is not really a coincidence because both men had climbed the same mountain. Neither of them proved the theorem by studying the primes directly. Both of them proved it by studying a completely different object, a function that, on its surface, has nothing to do with counting primes at all. That object was the Riemann zeta function, and the shape of the 1896 proofs tells you exactly how the primes and this function are wired together. Both Hadamard and de la Vallée-Poussin reduced the entire prime number theorem to a single statement about where this function is allowed to equal 0. The function has certain special inputs where its value drops to 0, and the whole question of whether Gauss's curve holds forever turned out to be identical to a question about the location of those zeros. Specifically, both men proved the theorem by showing that no zero of the function sits on one particular vertical line. Rule out zeros on that line, and Gauss's density law is forced to hold to infinity. Allow even one zero there, and it could fail. The chaos of the primes and the zeros of this function are not two separate mysteries. They are the same mystery, written in two different alphabets. Think about how odd that is for a moment. We started with the most concrete thing in mathematics, whole numbers. Which of them can be broken apart and which cannot? You could explain the question to a child with a handful of pebbles. And the deepest truth about those pebbles, the law governing how the unbreakable ones are spread across the number line, turned out to be locked inside the behavior of a smooth, flowing function that lives not on the number line at all, but out on a two-dimensional plane, and whose connection to the pebbles is anything but obvious. Nobody counting primes would ever have stumbled onto this by counting harder. The bridge had to be built deliberately, decades before Hadamard and de la Vallée-Poussin ever crossed it, by someone who saw that the secret of the primes was hiding somewhere the primes themselves never appear. Which leaves the prime number theorem in a peculiar position, and it is the position that sets up all the tension to come. The theorem is proven, fully, rigorously, no doubt about it. Gauss's curve tracks the primes forever, and the ratio does close on 1, guaranteed. But a theorem about a limit is a promise about the long run. It swears the estimate becomes proportionally perfect as you climb to infinity. It says nothing at all, about how far off the estimate is at any actual number you might name. The curve and the staircase lock together in the limit. Fine. At any given height, though, there is still a gap between them. The smooth guess and the real count do not match exactly. There is an error. And it turns out that the size of that error, not the estimate it corrects, is where the whole 167-year mystery has been hiding all along. How big is the gap between the guess and the truth? The prime number theorem promises the guess and the count agree in the long run, and then walks away without telling you the one thing you actually want to know. By how much are they off, right now, at the number in front of you? That gap, the difference between Gauss's smooth curve and the true prime staircase at any given height, is called the error term. And the error term, not the curve it corrects, is the real protagonist of this entire story. Everything from here forward is about its size. To see why the size of a mistake could matter more than the estimate itself, leave the primes for a minute and think about something you can hold in your hand. A coin. Flip a fair one 100 times and you expect about 50 heads. You will almost never get exactly 50. You might get 54 or 47. Flip it 1,000,000 times and you expect about 500,000 heads, and again you will miss, but here is the part that matters. You will not miss by much, and the amount you miss by follows a law as rigid as the expectation itself. The typical distance between what you got and what you expected grows like the square root of the number of flips. 100 flips, expect to be off by around 10, which is the square root of 100. 1,000,000 flips, off by around 1,000, the square root of 1,000,000. The miss grows, but it grows agonizingly slowly, far slower than the number of flips, so that measured as a fraction of the total, the coin looks fairer and fairer the longer you flip it. That square root is the fingerprint of honest randomness. When you add up a long run of independent little pushes, some nudging one direction and some the other, they do not pile up, they mostly cancel. Heads and tails work against each other, and what survives the cancellation is not the full count but roughly its square root. If the misses grew faster than the square root, faster than that, the coin would be drifting, biased, quietly loaded. If they grew slower, the coin would be suspiciously well-behaved, more balanced than chance allows, as if something were reaching in to correct it. Square root error is the exact signature of a process that is genuinely random and nothing more. Not too wild, not too tidy. It is the amount of disorder a fair system is entitled to, and no other amount fits. Now carry that idea back to the primes. Gauss's curve is the expectation, the smooth prediction of how many primes should have appeared by a given point. The true count is what actually appeared. The error term is the miss, and so the natural question, the one that turns out to be the deepest question in the subject, is how that miss behaves as you climb. Does it grow like the square root of the numbers involved? The way a fair coin's miss grows like the square root of the flips? Or does it grow faster, drifting, swelling, betraying some hidden bias in how the primes are laid out? Because think about what a square root error would actually mean here. It would mean the primes, for all their local chaos, are distributed as evenly as anything random could possibly be. It would mean their apparent disorder is not sloppiness, but the disciplined disorder of fair coins, deviating from Gauss's prediction by exactly the amount honest randomness permits, and never a hair more. The twins bunching, the deserts yawning open, all the jaggedness we saw up close would be revealed as the surface texture of a process that is, at its core, as balanced as a thing can be while still being unpredictable. The primes would be, in a precise and measurable sense, as random as they are allowed to be, not more disordered than chance, not less, exactly as much. And a faster error would mean the opposite, something almost more unsettling. It would mean that somewhere out in the numbers, the primes clump or thin in a way that outruns pure chance, that they carry a bias, a lean, a preference we have not detected because it only shows itself at scales beyond where anyone has counted. The staircase would eventually pull away from Gauss's curve by more than randomness could explain, and that excess would be a message. It would be the primes telling us they are not merely unpredictable but structured in some deeper, stranger way, following a rule that bends the count off true. One outcome says the primes are perfectly fair coins in disguise. The other says the coins are loaded, and we simply have not flipped them enough times to catch the tilt. This is the moment to say plainly what the Riemann hypothesis is going to turn out to be, even though we have not built the machinery to state it properly yet. At its heart, stripped of all the complex plane apparatus still ahead of us, the hypothesis is the claim that the error term stays as small as it possibly can. That the miss between the guess and the count grows like the square root of the numbers, and no faster. That the primes are fair coins. The most famous unsolved problem in mathematics, the thing that has resisted every mind that has come at it for 167 years, is at bottom a single question about the size of an error. Are the primes as well behaved as randomness allows, or is there a hidden lean out there that no one has yet found? But to even measure that error, to get a grip on the gap between the smooth curve and the jagged count, we need a tool that no amount of staring at the number line will ever hand us. The primes are scattered. The count is a staircase of 100 million separate steps. You cannot measure the deviation of that whole ragged structure by examining it one step at a time. You need something that can take in the entire number line at once and read the imbalance in it as a single quantity. That tool does exist, and it comes, of all places, from an infinite sum, a running total of fractions that seems at first to have nothing whatsoever to do with prime numbers, until you watch what happens when you try to add it up. How could adding fractions forever tell you anything about primes? Vinus, ride. Vinus, Vinus, Vinus. Take one, then add a half, then a third, then a quarter, then a fifth, and keep going down through every whole number forever, but with a twist. Raise each of those bottom numbers to some fixed power first. 1 plus 1 over 2 to that power, plus 1 over 3 to that power, on and on through all the counting numbers. Pick the power to be 2, and you are adding 1, plus a quarter, plus a ninth, plus a 16th. Pick it to be 3, and the terms shrink even faster. This sum, run over every whole number, is the beginning of the zeta function, and there is not a prime in sight. It marches through all the integers, the composite, and the prime alike, treating them identically, which makes what Euler did with it feel almost like sleight of hand. Leonhard Euler was looking at this sum in the 1730s, and he asked a question that changes everything. What if you factored it? Not the sum itself, but the whole infinite expression, the way you would factor a number into its primes. He found that this endless sum over every integer is exactly equal to a different endless expression, a product, and that product runs only over the primes. One factor for 2, one for 3, one for 5, one for 7, and nothing else. The composites vanish entirely. On one side, a sum that walks through all the numbers. On the other, a product built from primes alone. And they are equal, exactly, term for term, forever. To feel why that equality holds, you have to watch what the product is quietly doing. Each prime contributes a single factor, and that factor, when you expand it, is itself a little infinite sum. The factor for the prime 2 secretly contains 1, plus a term for 2, plus a term for 2 squared, for 2 cubed, every power of 2. The factor for 3 contains every power of 3, and so on for every prime. Now, when you multiply all those factors together, you have to pick one term from each prime's little sum and multiply your choices. Pick the power of 2 piece here, the power of 3 piece there, leave the rest as 1. Every possible way of choosing gives you 1 power of 2 times 1 power of 3 times 1 power of 5, and so forth. And that is precisely where the primes and the integers fuse. Because every whole number is a unique product of prime powers. That was the very first thing we established, back at the beginning, when we called the primes the atoms of arithmetic. 60 is 2 squared times 3 times 5, in one and only one way. So every single choice you make across the product lands on exactly one integer, and every integer gets built exactly once, by exactly one set of choices. Nothing is missed. Nothing is counted twice. The product over primes, expanded fully, reassembles itself into the sum over all integers, and the guarantee that this works, that no number appears twice and none goes missing, is nothing other than the unique factorization we proved at the very start. Euler's identity is not a trick. It is the fundamental theorem of arithmetic, written in the language of infinite sums. Sit with what that gives us. On the left, an object that knows nothing about primes, a plain sum crawling through the integers in order. On the right, an object made of nothing but primes. The equality is a bridge, and it lets you carry information in both directions. Anything you can learn about the smooth, well-behaved sum on the left, you can translate into a statement about the primes on the right. And the primes, remember, are the ones we cannot predict, cannot pin down, cannot write a formula for. But the sum on the left is tame. It is continuous. It is the kind of thing the tools of calculus were built to handle. Euler had found a way to reach the untouchable primes by way of an object that mathematics already knew how to grip. This is the deeper reason the 1896 proofs of the prime number theorem never touched the primes directly. They did not have to. Euler's bridge meant that every question about the distribution of primes could be smuggled across to the other side and asked as a question about this sum instead. Where the primes were jagged and lawless, the sum was smooth and analytic, and on the smooth side, you could bring the full weight of calculus to bear. The chaos of the primes run through the bridge became the analysis of a function. That is what Hadamard and de la Vallée-Poussin were really doing when they proved things about where the function equals 0. They were reading the primes through the only window that would hold still long enough to be studied. But Euler's bridge, as he built it, only stands on solid ground for part of its length, and this is the limitation that Riemann would eventually shatter. The sum only adds up to a finite, sensible answer when the power you raise everything to is bigger than 1. Push the power down toward 1, and the term stops shrinking fast enough. The sum swells without bound. It stops being a number at all. So Euler's identity, powerful as it is, lives on a restricted stretch of territory. It speaks only about powers greater than 1. And for the questions we care about most, the questions about the error term and the fine structure of the primes, that stretch is not enough. The interesting behavior is happening exactly where the sum breaks down. Which raises the question that pulls us straight into the next stretch of the climb. What is so special about the value 1? The place where this whole beautiful bridge suddenly gives out beneath your feet. I is CUI. Set the power in Euler's sum to exactly 1. 1 plus a half, plus a third, plus a quarter, plus a fifth, straight down through every whole number with no power at all. Every term is smaller than the one before. The pieces shrink toward nothing. And yet the total does not settle on any number. It climbs forever, past 10, past 100, past any figure you care to name, if you are only patient enough to add long enough. This particular sum has a name, the harmonic series, and its refusal to settle is the first crack in Euler's bridge. A medieval scholar named Nicole Oresme noticed you could bundle the terms into groups. Take the half by itself, then the next two terms, a third and a quarter. Each of those is at least a quarter, so together they clear a half. Then take the next 4 terms, a fifth through an eighth. Each is at least an eighth, and 4/8 make another half. Then the next 8 terms clear a half. Then the next 16. You can keep manufacturing half after half after half forever, because there is always a next block twice as long whose terms are just big enough to clear the bar, and an endless supply of halves adds up to infinity. The terms shrink, but they do not shrink fast enough to escape. Now nudge the power just a hair above 1, and the whole picture flips. Raise every bottom number, not to the first power, but to something barely larger, and the terms shrink a touch faster, and that tiny extra speed is enough to rein the sum in. Instead of climbing forever, it converges, closing in on a finite value. This is the knife's edge Euler's bridge is built on. On one side of the value 1, the sum is a real finite number, and everything he proved holds. On the other side, at 1 and below, the sum falls apart and means nothing. The line between a bridge that stands and a bridge that collapses is razor thin, and it runs exactly through the value 1. To feel how sharp that edge is, picture pouring water through a funnel. As long as the water arrives slower than the funnel can drain, the level in the funnel holds steady at some height. Speed the water up, past the drain's capacity, and the funnel overflows. The level runs away. No steady height exists. The power you raise the terms to is the drain rate. Above 1, the funnel drains fast enough, and the sum holds at a finite level. At 1 exactly, the water arrives at precisely the draining speed, the balance tips, and the level climbs without bound. The harmonic series is the funnel filled right at the tipping point where the faintest change decides between a finite answer and infinity. Remember what this sum secretly is. Through Euler's identity, the sum over all the integers equals the product over all the primes, and the value 1 is the exact place where the primes are dense enough, spread thinly enough, that their combined contribution neither quite converges nor quite escapes. The breakdown at 1 is the primes announcing their own density through the behavior of the sum. The funnel overflows at precisely the rate the primes thin out. The place where the bridge gives way is not arbitrary. It is where the arithmetic of the primes has been hiding all along, pressed up against that single value. Push the power the other way, up to 2, and Euler found something that made the rest of Europe sit up. The sum of 1 over every square, 1 plus a quarter plus a ninth plus a 16th, does converge. Everyone knew that much. The question was what it converged to. Some finite number, surely, but which one? The Bernoulli brothers, the best minds in the field, had thrown themselves at it and failed to find the value. It sat open for the better part of a century. In 1734, a 28-year-old Euler cracked it, and the answer stopped people cold. The sum comes out to pi squared divided by 6. Read that again, because it should not make sense. Pi, the number that governs circles, the ratio of a circle's circumference to its width, the most geometric constant there is. And here it comes, climbing out of a sum that has nothing to do with circles, nothing to do with geometry, a bare list of square numbers turned upside down and added together. There is no circle anywhere in the question. There is a circle sitting in the answer. That collision, geometry falling out of pure arithmetic with no invitation, was the first sign that this family of sums reaches into corners of mathematics no one expected it to touch. It is why these sums were worth taking seriously in the first place. They carry secret connections between worlds that look completely unrelated. But every one of these results, the finite value at 2, the collapse at 1, the pi that fell out of the squares, lives under the same ceiling. They all require the power to be greater than 1, or at least they require it to sit on the safe side of that edge. Euler could ask his questions only where the sum converged, and the sum converges only for powers above the tipping point. The entire region, at 1 and below, the region where the funnel overflows, was closed territory, off the map. And the deepest questions about the primes, the ones about the error term, about how the count deviates from Gauss's curve, were going to live precisely in that forbidden region, on the far side of the collapse, exactly where Euler's sum could not follow. Someone was going to have to find a way to ask about a sum in the very place where the sum does not exist. I didn't to the side as died. Before anyone could ask about the sum where it collapses, the sum had to be fed a stranger kind of number. Everything so far, every power we raised those terms to, was an ordinary number you could mark on a line. 1, 2, a hair above 1. Riemann's move, the one that opens the whole modern subject, was to let that power leave the line entirely and become a point on a plane. To ask what happens when you raise a number not to a real power, but to an imaginary one. That phrase, an imaginary power, sounds like nonsense until you see what it actually does. So start with the thing everyone already understands. A number raised to a real power grows or shrinks. 2 to the third is 8, bigger. 2 to the negative first is a half, smaller. Real powers stretch and squeeze along the line. That is the only thing they know how to do. An imaginary power does something entirely different. It does not stretch at all. It rotates. Feed a number an imaginary exponent, and instead of growing or shrinking, it spins around a circle, its size untouched, only its direction changing. Where does a rotation come from when we were only ever multiplying? The imaginary unit is defined as the square root of -1, the number that, multiplied by itself, gives -1. On the number line, there is no such thing. No real number squares to a negative, so this number cannot live on the line. It has to step off it, sideways, into a second dimension, and that sideways step is a quarter turn. Multiply by it once, you rotate 90 degrees. Multiply again, another 90, and you have turned a full 180, landing on -1, which is exactly what squaring it was supposed to give. The number that turns growth into rotation was built, from its first definition, to be a turn. When it climbs into an exponent, it drags that turning up with it, and multiplication becomes spinning. So now let the power in Euler's sum be a full, complex number, with 2 parts. A real part, the ordinary piece, still doing the old job of stretching and shrinking, controlling how fast each term's size shrinks as you march through the integers, and an imaginary part, the new piece, doing the new job, spinning each term around as you go. Every term in the sum stops being a plain shrinking fraction. It becomes a little arrow. The real part of the power sets how long each arrow is. The imaginary part sets which direction each one points. And crucially, because each term sits over a different integer, and the spinning depends on which integer you are at, the arrows all point different ways. 2 points one direction, 3 another, 5 another still, each rotated by its own amount. This is the thing that changes everything. Back when the powers were real, every term in the sum was positive. Every fraction pushed the total in the same direction, upward, and the only question was whether they piled up to infinity or settled somewhere finite. There was no possibility of cancellation, because nothing ever pulled the other way. Now, with the arrows pointing every which way, terms can cancel. An arrow pointing right can be undone by one pointing left. You are no longer adding a column of positive numbers. You are adding a scatter of arrows laid end to end, and where the old sum could only climb, this new sum can loop, can fold back on itself, can even close up and return near where it started. Picture the arrows laid tip to tail, one after another, the way you would add any set of directed steps. A term, then off in a new direction the next term, then another turn, another step. Think of a room full of clock hands, each sweeping at its own speed, and you chain them nose to tail. If the speeds are unrelated, the chain wanders off into the distance. But if the speeds are tuned just right, the hands can curl the chain around into a loop that comes back and meets its own beginning. The path closes. The arrows, added up, land you back at zero. That returning to zero, that perfect cancellation of 100 spinning arrows summing back to nothing, is not a curiosity. It is the single most important event in this entire story. And every zero of the function we are chasing is exactly this. A moment where the endless chain of arrows, each spinning at the pace set by its integer, conspires to close a loop and cancel to nothing. None of this cancellation was possible with real powers, and that is the whole reason Riemann reached for complex ones. With everything positive, the sum was a blunt instrument. It could tell you how much, and nothing more. Once the terms could point in any direction and interfere, the sum gained a second kind of behavior, an inner rhythm, a capacity for the terms to conspire and cancel that carries far more information than a plain total ever could. The imaginary part of the power is a frequency, a rate of spin, and asking how the sum behaves across all possible frequencies is asking something enormously richer than asking for a single number. It is asking about the resonances of the whole infinite arrangement of integers at once. But there is a catch, and it drops us straight into the problem Riemann had to solve. The rotation, all that spinning and canceling, changes the direction of the arrows. It does not, on its own, fix whether they shrink fast enough for the whole chain to have a finite length. That is still the job of the real part of the power, the old stretching and shrinking part. And the real part obeys the very same rule we hit before. Only when it sits above 1 do the arrows shrink quickly enough for the sum to converge to a definite place. So, handing the sum complex powers has bought us cancellation, interference, a whole new richness of behavior. It has not bought us 1 inch of new territory. The sum still only converges in that same region, real part greater than 1, the region we already knew. All the interesting cancellation, all the places where the arrows might close their loops and hit zero, is happening, or might be happening, out in the forbidden zone where the sum still refuses to add up to anything at all. Riemann needed to stand in a place the sum told him did not exist. How do you evaluate a sum in the exact region where the sum has no value? The way out of that trap is one of the strangest ideas in mathematics, and it rests on a fact about smooth functions that feels almost too good to be allowed. A smooth complex function, if it exists at all across a region, is held in place so rigidly by its own values that there is only ever one way to extend it past the edge of where you first defined it. Only one. Not a best choice among many. The single possible continuation. Forced. Unique. With no freedom left over. To feel why that rigidity is even possible, compare it to the freedom you have with ordinary curves. Draw a curve across a page, then cover half of it and ask someone to guess the hidden part. They cannot. It could bend anywhere. A curve is floppy. It can do one thing on the left and something completely unrelated on the right, and nothing about the visible half pins down the rest. Smooth complex functions are the opposite of floppy. The condition that makes them smooth in the complex sense, that they behave consistently as you approach any point from every direction on the plane, not just from the left and right, is so demanding that it welds the whole function into a single rigid piece. Know the function on any small patch, however tiny, and you know it everywhere it can possibly reach. The patch dictates the whole. That is the escape. Euler's sum defines a perfectly good, smooth function in the region where it converges, real part greater than 1. That region is a patch, and by the rigidity, that patch already determines, completely and uniquely, a smooth function across almost the entire plane, far beyond where the sum itself makes any sense. The sum was never the real object. The sum was just the first glimpse of a larger function, the part of it visible through the one window where the arrows happen to shrink fast enough to add up. The function itself extends far past that window, and it was there all along, waiting, fully determined by the sliver we could see. This process has a name, analytic continuation, and the name matters less than the picture. Think of restoring a fresco where a section of the wall has crumbled away. If it were an ordinary painting, you could invent anything for the missing patch, any figure, any color. But suppose the surviving paint obeyed a law so strict that the lines leading up to the gap allowed only one possible completion, every brushstroke in the lost region forced by the strokes around it. You would not be guessing at the missing piece. You would be reading it off, the way the visible edges demand. That is, analytic continuation. The values in the region where the sum works are the surviving paint, and they dictate, uniquely, the single lawful way to fill in everywhere else. Riemann filled it in. He carried the function off the safe patch and across the whole plane, into the forbidden zone where Euler's sum overflows and collapses. And out there, the extended function is smooth, finite, and perfectly well-defined, even though the sum that first described it is screaming nonsense at those same points. You may have heard that the sum of all positive whole numbers, 1 plus 2 plus 3 plus 4 forever, equals -1/12. Stated that way, it is simply false, and anyone who has added two numbers can see it is false. The whole numbers pile up to infinity. What is actually true is subtler and much stranger. The extended function, the continued one, when you evaluate it at the input that would have corresponded to that sum back in the convergent region, returns -1/12. But at that input, the original sum does not apply anymore. It broke down. The value you get is the value of the larger function, read off by continuation from the region where things behaved, not the value of the impossible addition. The number is real. The function genuinely takes that value there. It is just not the sum of anything. It is what the unique, lawful continuation is forced to equal at a point where the sum itself has no meaning at all. With the continuation in hand, the function now covers the whole plane, with exactly one exception. There is a single point where even the extension cannot save it. One place where the function blows up to infinity and no lawful value can be assigned. That point sits at real part 1, the very edge we found earlier, where the harmonic series overflowed. Everywhere else on the entire infinite plane, the function is now smooth and finite and fully determined, That one broken point is not a flaw in the method. It is the scar left by the primes, the mark of the place where their density presses the sum past saving. The function is whole except for the single wound at 1, and that wound is where the arithmetic lives. Now the payoff, the reason any of this labor was worth it. Out in the newly reached territory, the region Euler could never enter, the extended function does something the original sum never could. It hits 0. There are points, scattered through the forbidden zone, where this smooth function, fed the right complex input, comes out to exactly nothing. These are the zeros, and we glimpsed what they are back when we watched the spinning arrows close their loops. Each zero is an input at which the infinite chain of rotating terms, if you could still add it, would curl around and cancel itself to nothing. Now, through continuation, we can locate those zeros even in the region where the chain will not converge, because the extended function knows where they are even where the sum cannot reach. Some of them are dull and easy to find, sitting at the negative even numbers, showing up for a simple structural reason and telling us almost nothing. But the others, the ones that matter, fall inside a specific narrow band of the plane, and they arrange themselves with a regularity that has no business being there given how they were born. The primes were chaos. The sum that encodes them is smooth, and now the zeros of that sum, these points of perfect cancellation out in territory the sum cannot even enter, seem to line up along a pattern so precise that Riemann, staring at them in 1859, was willing to guess they obey an exact law. Where, on this vast plane, do those zeros actually fall? Start with the zeros that do not matter, because clearing them away is what makes the real ones visible. When Riemann's extended function is fed a negative even number, -2, -4, -6, and onward, it comes out to exactly 0 every time. These are genuine zeros, real points where the function vanishes, and there are infinitely many of them marching off down the negative side of the plane. And they are almost completely uninteresting. They are uninteresting because we know exactly why they are there, and the reason has nothing to do with primes. The continued function carries inside it a factor that swings positive and negative and touches 0 at each of those negative even inputs for a structural reason baked into the machinery of the continuation itself. They fall on a schedule. You can predict every one of them without knowing a single thing about arithmetic. Mathematicians call them the trivial zeros, and the word is doing honest work. Anything you can see coming that far in advance, anything that lands on so tidy a schedule, is not hiding a secret. The trivial zeros are the function clearing its throat. Set them aside. What is left, once you have swept the trivial zeros off the board, is everything the entire problem is about. Because there are other zeros, and they behave nothing like the tidy ones. They do not sit on the negative axis. They do not land on any schedule anyone has ever been able to write down. They appear out in the middle of the plane, in complex pairs, at heights that seem to follow no simple rule, and every last one of them is tangled up with the primes. These are the non-trivial zeros, and if the trivial ones were the function clearing its throat, these are the function actually speaking. The first thing to establish about them is where they are allowed to live. Remember that the original sum converges and stays safely away from 0 whenever the real part of the input is greater than 1, so no non-trivial 0 can sit out there. That whole half of the plane is forbidden to them, and by a symmetry in the function, a mirror relationship connecting each side to the other, the region to the far left is closed off too, except for the trivial zeros we already dismissed. What remains is a vertical band, a strip of the plane running between real part 0 and real part 1. Every non-trivial 0, every single one that carries information about the primes, is trapped inside that strip. The chaos has been herded into a corridor 1 unit wide. We began with prime numbers scattered across an infinite line with no visible pattern, deserts and twins and no formula in sight. Through Euler's bridge and Riemann's continuation, the entire mystery of their distribution has been transferred onto the locations of these zeros, and those zeros, wild as they are, cannot escape a single narrow band. It is as if you swept a beach with a metal detector, an endless beach stretching past the horizon in both directions, and found that every buried signal, every piece of metal in the whole expanse, was confined to one thin ribbon of sand, a single stride across. You would stop searching the beach. You would walk that ribbon. Everything is in the strip. And within the strip, the zeros arrange themselves with a regularity that is genuinely eerie, given where they came from. They climb the band in a rising sequence, higher and higher, each at its own height, and they come in mirror image pairs balanced above and below the real axis. As you list them by height, the first, the second, the 10th, the 1000th, they never quite fall into a formula, yet they never look random either. They are spaced with a kind of nervous evenness, never bunching too tightly, never leaving too wide a gap, as though each one were aware of its neighbors and keeping its distance. That spacing, that reluctance of the zeros to crowd each other, is going to turn out to be one of the deepest clues in the whole subject, but its full strangeness is still several steps away. For now, it is enough to see that these points, born from the chaos of the primes, do not behave chaotically at all. Now comes the observation that turns a band of scattered points into the most famous conjecture in mathematics. Locate the actual zeros, the real ones, computed for Riemann's function, and plot where they fall across the width of the strip. They could, in principle, sit anywhere in that one-unit band, some near the left edge, some near the right, some in between, scattered across the corridor at every possible depth. They are not scattered across it. Every non-trivial zero anyone has ever found sits on a single vertical line running straight up the exact middle of the strip, at real part 1/2, not near the middle. On it, zero after zero after zero, all threaded onto one perfectly straight line down the center of the band, as if the corridor, a full unit wide, were an illusion and the zeros only ever cared about its spine. That is the picture Riemann was staring at in 1859, and the question it forces is unavoidable. Why the center line? What could compel these points, born out of the most disorderly objects in mathematics, scattered through a two-dimensional strip with a whole width available to them, to line up along a single one-dimensional thread down the middle? There is no obvious reason the width of the strip should collapse to a line. The forbidden regions on either side explain why the zeros stay out of the far left and far right. Nothing yet explains why they would refuse the rest of the corridor and cling to its exact center. Riemann saw the alignment, and in a paper of only a few pages, he wrote down what it would mean if it held forever, and then admitted he could not prove it did. Everything from here, every computer that has ever hunted these zeros, every mind that has broken against this problem for 167 years, hangs on that one line. What did Riemann actually write on those pages? That he's must prove. In November of 1859, Bernhard Riemann was admitted as a corresponding member of the Berlin Academy, and the custom was to mark the honor with a paper. He submitted something short, only a handful of pages, dense past the point of comfort, on a subject he had never published on before, and would never publish on again. It was the only work on prime numbers he ever put into the world, and it quietly rebuilt the foundations of the subject. To see what he actually did, hold in mind the two objects we have been carrying. On one side, the prime staircase, the jagged step function counting primes, jumping up by one at each prime and flat between them. On the other, the smooth curve of Gauss, the running estimate that threads through the staircase but never matches it exactly, always off by that mysterious error. The gap between them was the thing nobody could pin down. Riemann's paper is, at its core, a single equation that closes that gap completely. It does not estimate the staircase. It reconstructs it, step for step, jump for jump, exactly. And the material he reconstructs it from is the zeros. His formula says, in effect, that the prime staircase is built out of two ingredients added together. The first is Gauss's smooth curve, the main trend, the part everyone already had. The second is a correction, and the correction is a sum with one contribution from every non-trivial zero in the strip. Each zero throws in its own piece, and when you add the smooth curve to the full pile of contributions from all the zeros, the ragged staircase reassembles itself perfectly. Gauss gave the average. The zeros supply every deviation from that average, every jump, every flat stretch, the entire jagged difference between the smooth guess and the real count. Stop and weigh what that means. The error term, the gap between guess and truth that we called the protagonist of this story, is not a vague fog of randomness. It is a precise sum over the zeros. Every wiggle in the way primes deviate from Gauss's curve is dictated, exactly, by where those zeros sit. The chaos of the primes and the positions of the zeros are not merely linked, the way we said loosely before. They are two encodings of the identical information. Hand me the complete list of zeros and I can, in principle, reconstruct precisely which numbers are prime, every last one, with no error at all. The primes were never truly disordered. Their order was simply written somewhere no one had thought to look, in the heights of a set of zeros out on a plane. We are used to formulas that approximate, that get close, that carry an error bar. This is not that. Riemann's formula, with the complete infinite set of zeros included, does not approximate the prime staircase. It equals it. On the nose, the smooth curve plus the zeros gives you the count of primes below any number exactly, not nearly. A jagged step function, all sharp corners and sudden jumps, is being assembled out of a sum of smooth contributions, and the corners come out perfectly sharp. The jumps land in exactly the right places because infinitely many smooth pieces, added with the right heights and rhythms, can conspire to produce something jagged. The staircase is not approximated by the zeros. It is composed of them. Think of a complicated piece of music, a full chord sustained, and imagine writing down the exact list of pure tones inside it. Each frequency, each volume. From that list alone, someone could rebuild the chord perfectly, because the chord simply is the sum of those tones. Nothing about it is left over once you have them all. Riemann's formula says the prime staircase works the same way. Each zero corresponds to one pure tone, and the primes are what you hear when all those tones sound together. Get one tone wrong, one zero misplaced, and the reconstruction distorts. The primes come out subtly off. The whole distribution of the primes is a chord, and the zeros are its notes. Which is exactly the point at which Riemann wrote the sentence that has outlived everything else in the paper. Looking at these zeros, at the way every one he could locate sat on that center line down the middle of the strip at real part 1/2, he remarked that it seemed very probable that all of them do, that every non-trivial zero, without exception, all the way up the infinite band, lies on that single line. And then, in a phrase that has haunted the subject for over a century and a half, he set it aside. He wrote that he had looked for a proof, had not found one after some fleeting attempts, and that it was not necessary for the immediate purpose of his paper, so he moved on. He guessed the deepest structural fact about the primes almost in passing, admitted he could not establish it, and continued to his other business. He may not have grasped, that afternoon in Berlin, that he was leaving behind the question that would define the next 7 generations of his field. But look at what the sentence is really claiming. now that we have the formula. If every zero sits on that center line, then every note in the chord has a specific, balanced character, and the error between the primes and Gauss's curve is held to the smallest size it could possibly take. The center line is not an aesthetic preference of the zeros. It is the precise condition that would make the primes as evenly distributed as randomness allows, the fair coin behavior we chased chapters ago, now revealed as a statement about the geometry of a line. So the guess comes down to this. What does it actually take, note by note, for a zero to sit on that line rather than off it? And why would the entire infinite chord agree to stay in tune? Take a single zero out of the strip and ask what it actually contributes to the prime count, because until you see one zero working alone, the chord means nothing. A zero is a point on the plane, so it has two coordinates. A left-right position, its real part, telling you how far across the strip it sits, and a height, its imaginary part, telling you how far up the band it has climbed. Each of those two numbers does a specific job in the reconstruction, and the jobs are different. The height, the imaginary part, sets a frequency. When that zero throws its contribution into the sum that builds the staircase, the contribution is not a static lump. It oscillates. It rises and falls as you move along the number line, a wave rolling across the integers, and the height of the zero is exactly the pitch of that wave. A zero low down in the strip produces a slow, long wavelength oscillation, a lazy swell that takes a long stretch of numbers to complete one cycle. A zero high up produces a rapid, tightly packed wave that ripples through the numbers quickly. Every zero sings a note, and how high the zero sits is how high the note sounds. The other coordinate, the real part, the left-right position, does something quieter but more decisive. It sets how loud the wave is, and more than that, whether the wave holds steady or swells as you climb the number line. This is the coordinate the whole hypothesis is about, so it is worth being precise. A zero's real part controls the amplitude of its wave in a way that grows with the size of the numbers you are counting through. Push a zero even slightly to the right of the center line, and its wave grows louder, faster as you climb. Nudge it left, and the wave stays quieter. The horizontal position is a volume knob, and it is a volume knob that gets turned up the further out you count. Now put those two rolls together, and you can read any single zero as a complete instruction. Its height tells you the frequency of a wave. Its horizontal position tells you how loudly that wave sounds and how fast the loudness builds. 1 0, 1 wave, fully specified by where it sits. And Riemann's formula says the deviation of the primes from Gauss's smooth curve, the entire error term, is nothing but all of these waves, 1 per 0, laid on top of one another and added up. The jagged error we could not predict is a sum of waves, not a metaphor for a sum of waves. An actual sum, each wave contributed by 1 point out on the plane. To feel how a pile of smooth waves can carve something as sharp as a staircase, watch them accumulate. Start with just the first zero, the lowest one, and add only its single slow wave to Gauss's curve. You get the smooth curve with one gentle ripple laid over it, nowhere near the real staircase, but leaning in the right direction, bulging up roughly where the primes are denser and sagging where they thin. Add the second zero's wave. The combined ripple gets a little more detailed, tracking the true count slightly better. Add the 10th, the 100th. With each wave you fold in, the sum sharpens. The lazy ripples begin to interfere, reinforcing each other exactly at the primes and canceling exactly between them, and what was a soft, undulating curve slowly stiffens into steps. Corners emerge. Flat stretches flatten. The jumps grow steeper and land in the right places. The mechanism doing that sharpening is interference. The same thing that happens whenever many waves share a space. Where the waves happen to agree, all cresting together, they add into a strong spike. Where they disagree, crest against trough, they flatten to nothing. The zeros are tuned by their heights and positions, so that all their waves crest together at precisely the prime numbers and cancel everywhere else. A single wave could never locate a prime. It is too smooth, too spread out, but thousands of them, each contributing its sliver, interfering constructively at one exact integer and destructively at its neighbors, can pin a jump to a single number. The precision of the primes is built out of the cooperation of a vast choir of imprecise waves. No one voice knows where a prime is. The whole ensemble, interfering, knows exactly. Imagine a sound desk with a long row of sliders, each slider feeding in one pure tone at one pitch and volume. Start with them all down, and you have Gauss's smooth curve, featureless. Now raise the sliders one at a time, lowest pitch first. At first you hear a vague hum, a wash of tone with no articulation. But as more and more sliders come up, the tones begin to interlock, and out of the wash, something structured emerges. Edges, definition, until with the full bank raised, the blur resolves into something crisp and exact. The primes are what the sound desk produces with every slider raised. Each zero is one slider. The staircase is the sound of the complete arrangement, every note present, every volume correct, all of them interfering into a shape that is somehow all sharp corners despite being made entirely of smooth tones. We began among the primes convinced they were chaos, unpredictable, formula-proof, scattered without law, deserts and twins and no way to guess the next one. They were never chaos. Every prime sits exactly where the interference of this choir of waves places it. And the choir is not random. Its notes are the zeros, and the zeros, as we saw, are not scattered across the strip. They cling to that one center line with a discipline that looks almost enforced. The apparent disorder of the primes is the sound of a perfectly ordered set of waves. The chaos was the music. The order was the sheet it was written from. Which turns the entire question inward, onto the one thing we have not yet forced. If the primes are this choir, and the choir sounds balanced only when every note holds a specific character, then everything depends on whether the zeros truly all sit on that line. What happens to the music if even one of them does not? Now the sentence Riemann set aside can be stated with the full weight it deserves. The Riemann hypothesis is the claim that every non-trivial zero of the zeta function has real part exactly 1/2. That every note in the chord of the primes sits on the center line of the strip, not one of them off it, all the way up the infinite band, forever. That is the whole of it. One sentence about the horizontal position of a set of points. Stated that way, it sounds almost modest, a technical remark about coordinates, and its enormity only appears when you carry it back through everything we have built. Recall what the real part of a zero controls. It is the volume knob, the coordinate that sets how loudly each zero's wave sounds and how fast that loudness grows as you count higher. And recall the specific behavior of that knob. A zero exactly on the center line produces a wave whose amplitude grows like the square root of the numbers you are counting through. Not faster. That is precisely what sitting at 1/2 does to the loudness. So if every zero sits on the line, every wave in the choir grows at that same measured square root rate, and the total error, the whole pile of waves added together, is held to square root size. And square root size is exactly where this story began, with a coin. That was the fingerprint of honest randomness. A fair coin flipped a great many times drifts from perfect balance by about the square root of the number of flips, no more. We said back then that the deepest question in the subject was whether the primes deviate from Gauss's curve by that same square root amount, the amount a fair coin is entitled to, or whether they drift further, betraying some hidden bias. The Riemann hypothesis is the answer to that question, translated into geometry. Every zero on the center line means every wave grows at the fair coin rate, which means the primes deviate from their expected count by exactly as much as honest randomness allows, and not a hair more. The hypothesis is the claim that the primes are fair coins. The center line and the fair coin are the same statement wearing two different costumes. The primes are not random. Every one of them is fixed, determined, sitting where it has always sat, decided entirely by the rigid rules of multiplication. There is nothing uncertain about whether 17 is prime. It simply is, and always was, with no chance involved. And yet, the hypothesis claims these utterly determined objects are distributed exactly as if each one had been placed by the flip of a fair coin. They pass the test for randomness perfectly while being the least random things imaginable. The primes are what you would get if pure determinism and pure chance turned out to produce, at the largest scale, the identical pattern. Hold both of those facts at once. On one side, the primes are locked in place by definition, carrying no randomness at all. On the other, the hypothesis says their large-scale scatter is statistically indistinguishable from the fairest coin ever flipped. A thing can be completely determined and completely balanced at the same time, and the primes, if Riemann was right, are the supreme example. This is not a claim that the primes are almost random, or random enough for practical purposes. It is the claim that they are as balanced as it is mathematically possible for anything to be, that the disorder we saw up close is not sloppiness but the tightest, most disciplined disorder there is. Order so complete, it is indistinguishable from perfect chance. Imagine a vast choir, thousands of voices, each singing one sustained note, and imagine the condition that no single voice is louder than any other by even the faintest degree. Every voice contributes, none dominates, and the sound they make together is smooth, precisely because the balance is perfect. That is what all the zeros sitting on one line amounts to. Each wave grows at the same rate, so no single zero's wave ever swells up and overpowers the rest. The choir stays balanced forever, and the smoothness of the prime's large-scale behavior, the reliability of Gauss's curve, is the sound of that perfect balance. Let even one voice begin to swell louder than the others, and the balance is broken, and the smoothness with it. Which is why the hypothesis is not just true or false the way most statements are, but true or false in a strangely fragile way. It is a claim of total order, and total order tolerates no exceptions. Every zero must be on the line. Not almost every zero, not the first 10 trillion, every single one, without a single stray, up an infinite band that never ends. A claim like that has a peculiar vulnerability built into it, an asymmetry we are about to walk straight into. To confirm it, you would have to somehow account for infinitely many zeros at once, an impossible census. To destroy it, you would need only one zero, anywhere in that endless strip, sitting even a hair off the center line, and the whole edifice of perfect balance collapses. So the entire weight of the most balanced structure in mathematics rests on a condition that a single point could violate. Everything we have followed, the fair coin, the square root error, the choir in perfect tune, the primes as ordered chaos, all of it holds only if not one zero out of infinitely many ever steps off the line. And that raises the question that turns this from a beautiful picture into a genuine abyss. We have been assuming, this whole time, that the balance holds. Riemann assumed it. The picture is gorgeous if it holds. But what would actually happen to the primes, to the choir, to everything, if somewhere far out in that infinite band, one single zero had wandered off the line? Suppose one zero has wandered off the line. Not far. A hair to the right of center, somewhere so high up the strip that no one has ever counted that far. Everything else stays where it should. Infinitely many zeros, all obediently on the center line, and one lone defector standing slightly to their right. Follow what that single misplaced point does to everything downstream, because it is not a small local blemish. It rewrites the primes. Return to the volume knob, the real part, and what being off-center does to a wave. A zero exactly on the line grows like the square root of the numbers, the fair coin rate, matched to all its neighbors. A zero pushed to the right grows faster than that. Its wave swells louder and louder as you climb, outpacing the square root ceiling, and because the horizontal position is a knob that gets turned up the higher you count, the further out you go, the more this one voice drowns the others. The choir was balanced only because every voice grew at the same rate. Introduce one voice that grows faster, and it does not merely add a little noise. Given enough distance, it swells until it is louder than the entire rest of the choir combined. And a choir with one runaway voice no longer sings a balanced note. The primes, remember, are the sound of the choir. Their smooth agreement with Gauss's curve is the sound of every wave staying in proportion. Let one wave grow without that restraint, and the error term, the deviation of the primes from the smooth curve, stops behaving like a fair coin's drift. It swells past square root size. The primes begin to clump or thin, far out in the numbers, by more than randomness could ever account for. There would be long stretches where primes crowded in beyond any fair expectation, and long stretches where they thinned out past what chance permits, a slow tidal bias rolling through the number line, driven entirely by that one wave that would not stay quiet. The primes would carry a lean, and the source of the lean would be a single point, sitting a hair off a line, impossibly far away. This is the asymmetry we saw coming. To prove the hypothesis true, you must somehow guarantee that not one zero out of an endless supply ever steps off the line. An infinite verification, every voice checked forever. But to prove it false, you need to find one. A single rogue zero, exhibited once, and the whole claim of perfect balance is dead. Truth here requires accounting for infinity. Falsehood requires a single counterexample. The two are not symmetric labors, and that imbalance is part of why the problem has the grip it does. Everyone who has ever hunted these zeros has been, in effect, looking for that one defector, knowing that finding it would end the question in an afternoon, and that failing to find it, no matter how long the search, proves nothing at all. It is often said that if someone proved the Riemann hypothesis false, the world's encryption would shatter, banks would fall, secrets would spill. This is mostly wrong, and seeing why sharpens what the hypothesis actually touches. The encryption that guards a message online leans on a different hard fact, that multiplying two enormous primes together is easy, while pulling the product back apart into those primes is monstrously slow. That difficulty stands or falls on its own. It does not depend on where the zeros sit. A proof that a zero lies off the line would not hand anyone a fast way to factor a number. The locks would hold. Over more than a century, mathematicians have built an enormous body of results that all begin with the same phrase. Assuming the Riemann hypothesis is true, then such and such follows. Hundreds of theorems, whole regions of number theory, constructed on the presumption that the balance holds, waiting for the foundation to be confirmed. If the hypothesis is true, all of that scaffolding becomes solid ground at once, an entire conditional continent turned real. If it is false, that same continent does not simply vanish, but every result resting on it has to be re-examined, and the precise control we thought we had over the primes turns out to be an illusion we leaned on for generations. The stakes are not one dramatic collapse. They are the quiet truth or falsehood of a vast web of things we have already allowed ourselves to believe. And underneath the practical stakes sits something that does not depend on any application at all. The hypothesis is a statement about whether the deepest layer of arithmetic is orderly or not. Whether the primes, the atoms from which every number is built, are laid down with perfect balance or carry a hidden flaw. That question has weight whether or not a single theorem or a single lock depends on it. It is asking whether the foundation of counting itself is sound. A single zero off the line would mean the integers harbor a bias at their core, a lien built into the raw material of mathematics, invisible until you climbed high enough to feel it. Most who study this believe the balance holds. They believe it because every zero ever found obeys, and because the alternative feels like a wound in something that ought to be whole. But belief is not proof, and the primes owe us nothing. So the question becomes a search. If a single rogue zero would settle everything, and if it could be lurking anywhere in an infinite strip, then the obvious move is to go looking. Check the zeros, one after another, as high up the band as human ingenuity and machinery can reach, and see whether every one of them sits on the line or whether, somewhere out there, one has strayed. People have been checking for a very long time, with pencil, and then with the most powerful machines ever built. The question is how far they have gotten, and whether all that checking has brought us even one step closer to the thing a search like this can never quite deliver. The first real progress on Riemann's guess came 55 years after he made it, and it is a perfect lesson in how this problem refuses to be satisfied. In 1914, the English mathematician Godfrey Harold Hardy proved that infinitely many of the zeros lie exactly on the center line, not a few, not the first several thousand. Infinitely many, guaranteed, forever. It sounds like the case is closed. It is not, and the reason why is the whole trap of the subject in miniature. The catch is that infinitely many is not the same as all. This is one of those places where ordinary intuition, built for finite piles, quietly fails you. You can have an infinite collection sitting on the line and still have infinitely many others scattered off it, because infinity leaves room for both. Picture the even numbers. There are infinitely many of them, an endless supply, and yet they make up only half of all the whole numbers, with the odd numbers equally infinite, filling the other half. Proving an infinite crowd of zeros sits on the line is like proving there are infinitely many even numbers. True and real progress, and still completely silent about whether something else, equally infinite, lives off the line. Hardy pinned down an endless set of well-behaved zeros. He could not rule out an endless set of rebels hiding among them. So the theorists chipped at the proportion instead. If you cannot show all the zeros are on the line, show that at least some fixed fraction of them are, and then push the fraction upward. Over the following century, that fraction was forced higher, a third of the zeros, then 2/5, then a bit beyond, each improvement a serious piece of work. But notice what that project can never do. Pushing the fraction toward 100%, even getting agonizingly close, still leaves a sliver unaccounted for, and a single zero in that sliver would end everything. You cannot reach all by climbing through fractions. There is always a last gap, and the rogue could always be in it. The proportion approach, for all its ingenuity, is structurally incapable of finishing the job. While the theorists worked the proportions, everyone else just started counting zeros directly, and the machines eventually took over. Locate the zeros one by one, climbing the strip, and check each against the line. Riemann himself computed the first few by hand. Then better methods. Then early computers. Then enormous dedicated calculations, marching up the band, zero after zero, verifying each one. The count now stands past 10 trillion. More than 10 trillion non-trivial zeros have been located and checked, climbing higher up the strip than Riemann could have dreamed, and every single one of them, without exception, sits exactly on the center line. 10 trillion. If you tried to look at 1 zero every second, without sleeping, it would take you longer than 300,000 years to work through the ones already checked. And in all of them, not one defector, not a single zero off the line. Faced with 10 trillion perfect confirmations and no exceptions, almost anyone would conclude the matter is effectively settled. The temptation is overwhelming. 10 trillion consecutive successes is a level of evidence that would count as certainty in nearly any other domain of human knowledge. If a coin came up heads 10 trillion times, you would stop believing it could ever come up tails. But mathematics does not grant that kind of certainty, and this problem in particular has a way of punishing anyone who trusts a big number. Because 10 trillion against infinity is nothing. It is not a large fraction of the zeros. It is not a small fraction. It is not a fraction at all. It is a finite pinch taken from an endless supply. And the entire question is about what happens out where no machine has ever reached, in the infinite remainder that no amount of counting will ever touch. Recall Gauss's smooth curve, the running estimate for the prime count. For every number anyone has ever checked, that curve sits slightly above the true count of primes. Every single computed value. It looks, from all the evidence, like an unbreakable rule. The curve always a hair too high. It is not a rule, Littlewood proved, in that same year, 1914, that infinitely far out the two must cross, that eventually the true count overtakes the curve and the relationship flips, and then flips back, endlessly. The crossover has never been seen, because the number where it first happens is so enormous it dwarfs anything the physical universe could store. But it is out there, guaranteed by proof, a place where the obvious pattern of every computed case simply reverses. The primes handed us a rule that held for every number we could reach, and was false anyway. The lesson is not subtle. In this domain, 10 trillion agreements is a suggestion, not a verdict. The hypothesis has been confirmed more thoroughly than almost any unproven statement in the history of mathematics, 10 trillion times over, with a perfect record. And that record, however staggering, is logically worth precisely nothing as a proof. It cannot be worth anything, because the claim is about an infinite set, and no finite search, however vast, can speak for infinity. Verification, in this problem, is not a slow approach towards certainty. It is a different kind of thing altogether, and it never converges on proof no matter how long it runs. We could check for another 300,000 years and be exactly as far from a proof as we are now, which is to say, infinitely far. We do not want more confirmations. Another trillion zeros on the line would tell us nothing we do not already believe. What we want is a reason, some argument that explains why the zeros must lie on the line, that reaches the infinite remainder no machine can visit, that turns 10 trillion lucky agreements into a necessity. And for a long time, no one had the faintest idea where such a reason might come from. The proof, if it exists, was not going to be found by counting harder. It was going to have to come from somewhere else entirely, from some other part of the world of ideas that no one had thought to connect to the primes. As it happened, the most promising clue anyone has ever found arrived by accident in a common room over a cup of tea between two people who had no business having the same numbers in their heads. Now they have. Afternoon tea, April of 1972, in the common room of the Institute for Advanced Study in Princeton. A young number theorist named Hugh Montgomery, in town to discuss something else, fell into conversation with the physicist Freeman Dyson, whom he had just met. Dyson asked what he was working on. Montgomery started to describe the spacing of the zeros, and within a minute, the two of them realized they had been staring at the same equation from opposite ends of science. To understand what collided that afternoon, you have to know what Montgomery had been measuring. Not whether the zeros sit on the line, something finer. He was studying how the zeros are spaced relative to each other as they climb the strip. Not their individual positions, but the statistics of the gaps between them. Are neighboring zeros bunched or spread, or laid down at random like raindrops on pavement? And he had found they were none of those. The zeros were spaced with a peculiar discipline. They seemed to avoid each other. Wherever two zeros came close, something pushed them apart, so that tight pairs were rarer than pure chance would produce. He had written down a formula, a curve describing exactly how strongly the zeros repel their neighbors. That word, repel, is the hinge, so hold on to the picture behind it. If you scatter points completely at random along a line, they clump. Pure randomness produces plenty of near collisions, points landing almost on top of one another, just by chance. Montgomery's zeros refused to do this. Between any two of them, there was a kind of invisible spring, a mutual avoidance, thinning out the close pairs and holding the zeros at a more even distance than randomness alone would ever allow. His formula was the precise mathematical shape of that avoidance. And it was this formula he began describing to Dyson over the tea. Dyson recognized it instantly, because he had written essentially the same formula years earlier about something with no conceivable connection to prime numbers. Atomic nuclei. The heavy ones, uranium and its neighbors, are so complicated inside, so many protons and neutrons churning against one another, that no one can calculate their energy levels directly. The interior is a storm too tangled to solve. So physicists had given up solving it exactly and started treating the nucleus statistically, modeling its behavior with large matrices full of random numbers and studying the properties those random systems tend to have. Out of that work came a formula for how the energy levels of a heavy nucleus space themselves, and those energy levels, it turned out, also repel each other. They avoid crowding, hold themselves apart, thin out their close pairs, according to a curve, the exact curve Montgomery had just written on the board for the zeros. Let the strangeness of that land fully. On one side, the zeros of a function built from the prime numbers, the most abstract objects in pure thought, defined by nothing but arithmetic. On the other, the energy levels of a lump of uranium, a physical thing you could hold, governed by the churning of subatomic particles, two systems that share not a single ingredient, not a concept, not a piece of machinery, and their internal statistics, the way their pieces space themselves, are described by the identical formula. The zeros of the primes and the quantum states of heavy matter are spaced the same way. Nobody predicted this. Nobody had any reason to look for it. It fell out of a chance remark over tea between two people who happened to recognize each other's numbers. This was not a fluke of a small sample either, which is what makes it impossible to dismiss. In the years that followed, Andrew Odlyzko pushed the test to a scale that removes any doubt. He computed the zeros not near the bottom of the strip, but astronomically far up it, near the 10 to the 20th zero and beyond, and measured the spacings of millions of them. Then he laid that data against the curve from the physics of random matrices. The match was almost perfect. Millions of zeros, climbing a region of the strip so high that Riemann could not have imagined reaching it, spacing themselves exactly as the energy levels of heavy nuclei do, tracking the theoretical curve so closely that on a graph, the mathematics and the physics become a single line. The connection is not a coincidence of the first few zeros. It holds, with staggering precision, as far up as anyone has been able to compute. And this transforms what kind of problem the Riemann hypothesis even is. Up to this point, the zeros lying on a line looked like a fact about a particular function, a quirk of one specific object in analysis. Now they looked like something else, Systems whose components repel each other with that exact signature are almost always one kind of thing. They are the energy levels, the resonances, of some underlying physical system. The pattern Montgomery found is the fingerprint that a set of numbers is the spectrum of vibrations of a real, if hidden, instrument, which raises a possibility that had been whispered decades earlier but now grew teeth. Perhaps the zeros lie on the line not because of some accident of arithmetic, but because they are the energy levels of a physical system nobody has found yet. A system whose vibrations are the zeros and whose very existence would force them onto the line automatically, the way a real physical spectrum is always real. So the question quietly changed its shape. For a century it had been, why do these zeros lie on a line? After the T, it became something stranger and more concrete. Is there an instrument, somewhere in the space of mathematical objects, whose natural frequencies are exactly the zeros of the primes? Find that instrument, show its vibrations must be the zeros, and the hypothesis would fall out as a consequence of the instrument being real. The primes, the uranium nucleus, the random matrices, all of them were pointing at the same hidden object, an object no one had yet held. The search stopped being a hunt for a proof in the usual sense and became a hunt for a thing. What could that instrument possibly be? Macon Goddard down, his working down. The idea that the zeros might be the vibrations of some instrument was not born at that T. It had been sitting in the field for half a century already, proposed independently by two mathematicians, David Hilbert and George Polya, sometime in the early 1900s, as little more than a hunch. What the T did was hand that half-century-old hunch a piece of hard evidence, and suddenly a vague dream looked like a lead worth chasing. To see why the dream would solve everything, you need one fact about a certain kind of physical system, and it is the whole reason the idea has teeth. Some systems, the ones physicists call self-adjoint, have a property that is not optional or approximate, but forced by their structure. Their natural frequencies, the energies at which they resonate, are always real numbers, never imaginary, never off in some other direction. The mathematics guarantees it. A drumhead cannot vibrate at an imaginary pitch. The frequencies of a real, stable, physical system are locked onto the real axis by the very definition of what makes the system stable. That guarantee is not a tendency. It is a theorem. Build a system of the right type, and its frequencies have no choice but to be real. Now lay that guarantee against what the Riemann hypothesis asks. The hypothesis wants every zero to sit on the center line, which is to say, it wants a particular quantity attached to each zero to come out real, with no imaginary drift, for all of them, forever. And we have just seen that a certain kind of physical system produces frequencies that are forced to be real, automatically, with no exceptions, by its structure alone. Put those two together, and the strategy writes itself. Suppose someone could build, or discover, a self-adjoint system whose natural frequencies are exactly the zeros of the zeta function. Then the zeros would be frequencies of a stable physical system, and frequencies of such a system must be real, and real is precisely the condition of lying on the line. The hypothesis would not need to be checked zero by zero. It would follow, all at once, from the existence of the instrument. Every zero on the line, guaranteed, because that is what the frequencies of that kind of instrument are always compelled to be. Counting zeros could never reach infinity. Pushing the proportion toward 1 could never close the final gap. Both were doomed to fall short because they worked 1 zero at a time, or 1 fraction at a time, against an endless supply. The instrument does not work that way. It would prove the whole infinite collection in a single stroke, not by visiting the zeros but by identifying what they collectively are. You would never touch an individual zero. You would show that all of them together are the spectrum of one object, and the object's nature would take care of the rest. It is the difference between checking that every soldier is standing on a line and discovering they are all bolted to the same rail. For a long time, this was pure aspiration, a lovely idea with nothing behind it. The T in 1972 changed that, because the spacing statistics gave the dream a specific target. The zeros do not just need to be somebody's frequencies. They space themselves exactly like the energy levels of a particular family of systems, the ones without time reversal symmetry, the ones whose internal churning has a direction to it. That narrowed the search enormously. Whoever the hidden instrument is, it must belong to that specific class, must have that particular kind of internal complexity, the same class that describes a heavy nucleus with its irreversible churn. The mathematicians hunting the instrument were no longer looking for anything at all. They were looking for a very specific kind of thing, with a known signature that happened to have the primes buried in its resonances. The most promising direction came to be called quantum chaos, and it sharpened the picture further, though it has never closed it. The systems whose energy levels repel that way tend to be the quantum versions of physical systems that, in ordinary mechanics, are chaotic, motion so sensitive that its path is unpredictable even though its rules are fixed. A ball bouncing forever around a strangely shaped billiard table, never repeating, is the classic image. Quantize such a system and its energy levels arrange themselves with exactly the repulsion the zeros show. So the hidden instrument, if it exists, is likely the quantum echo of some chaotic classical motion, some abstract analog of a particle rattling around a peculiar space, whose allowed energies are the zeros of the primes. Researchers have even identified suggestive fragments, expressions from the physics of such systems that mirror expressions from the theory of the zeros, close enough to feel the object breathing on the other side of the wall. But no one has found it, and the honest state of things is that the instrument remains entirely hypothetical. Every clue points to its existence. The spacing statistics match to staggering precision. The half-century-old structural argument that would make it work. The fragments from quantum chaos that echo the right formulas. It all feels like standing outside a room and hearing an instrument being played, the sound unmistakable, the melody clearly coming from somewhere just beyond the door. And then you open the door, and the room is empty. The music is real, the evidence of the instrument is everywhere, and the instrument itself is nowhere to be found. No one has written down the system. No one has proven it exists. The resonances are there without any resonator anyone can point to. Which leaves this whole beautiful approach in a maddening position, and it is worth stating plainly because it defines where the problem actually stands. We may have discovered what kind of thing the answer is without being able to produce the thing. The evidence that the zeros are a physical spectrum is overwhelming, and overwhelming evidence, as this problem has taught us again and again, is not proof. The instrument would prove the hypothesis in a single stroke if it existed, and its existence is exactly what no one can establish. After the T, after the matching statistics, after 50 years of quantum chaos, we are left listening to music through a door that will not open. And so the real question is no longer only where the zeros lie, but why, after 167 years and a clue this strong, the door has stayed shut. What is it about this problem that lets it hand us the answer's shape and still refuse the answer? Conductive life. For 167 years, essentially every mathematician of the first rank has, at some point, turned to look at this problem. Hilbert placed it on his famous list of the great unsolved questions at the dawn of the 20th century. Hardy carried it with him for decades. Selberg, Bombieri, Conry, a long line of the finest number theorists alive, gave large pieces of their careers to it, and the honest summary of all that effort is that no one has come close. Not close in the way that a hard problem is usually approached, with the distance to the summit shrinking year by year. The distance has barely moved. Look first at what the direct assault has managed. Long ago it was shown that no zeros sit on the far right edge of the strip, the line that gave us the prime number theorem. Since then, the proven zero-free zone has been pushed a little way inward, carving out a thin sliver near that right edge where no zero can hide. But that sliver is almost grotesquely thin, and it has grown almost imperceptibly in over 60 years. The best result anyone has, the frontier that the hardest analytic work has reached, is still an enormous distance from the center line the hypothesis is about. We have proven the zeros avoid a narrow strip near one edge. We are nowhere near proving they crowd onto the line down the middle. Between the frontier and the goal lies almost the entire width of the problem, untouched. The proportion results tell the same story from another angle. Rather than clearing a region, this approach asks what fraction of all the zeros can be shown to lie on the line. Decades of ingenuity carried that fraction from nothing to a third, then to 2/5, then a little beyond. Serious achievements, each one. And each one is also a reminder of how far there is to go, because a fraction, however large, is not all. You can push it to 40%, to 45%. And the gap to 100 remains a chasm no fraction can cross. Worse, a single zero in the uncovered remainder would destroy everything. So even 99% proven would leave the actual question wide open. The proportion climbs, and the target does not get closer. Because the target was never a percentage, it was totality. And totality is a different kind of thing. Then there are the announced proofs, and their history is its own kind of lesson. More than once, a serious mathematician has stood up and claimed the problem solved, and more than once the claim has dissolved under scrutiny. In the late 1940s, a respected analyst's disproof was reported in the press before a flaw was found and the whole thing collapsed. In more recent years, a celebrated figure, late in a great career, presented a short proof leaning on an idea from physics, and the community, gently and sadly, did not believe it. Others have circulated approaches that looked promising for years until a counterexample showed the road did not go through. These are not stories of carelessness. They are stories of first-rate minds breaking against something that yields the appearance of progress and then, on close inspection, takes it all back. The problem has a way of looking solvable from a distance and closing up the moment you arrive. So, the real question is not who has tried, but what exactly is missing, and here the field has arrived at a sobering kind of agreement. The trouble is not that mathematicians lack the technical strength to push the existing methods harder. They have pushed those methods to exhaustion. Refining the current tools yields another decimal place on the zero-free region, another percent on the proportion, and nothing that reaches the line. The consensus, insofar as there is one, is that the existing approaches are not almost good enough. They are the wrong kind of tool entirely. Grinding them finer will never close the gap, because the gap is not a matter of degree, it is a matter of kind. What is missing is not more force. It is a genuinely new idea, some conception of why the zeros must lie on the line that no one has yet had. Imagine a high wall, and imagine that every ladder anyone has ever built to scale it comes up short by exactly one rung. Not close to the top, one rung short, every single time, no matter how the ladder is designed. When that keeps happening, ladder after ladder, decade after decade, you begin to suspect the problem is not the length of your ladders. You suspect the wall is not meant to be climbed at all, that what you actually need is a door, some entrance of a completely different character that the ladder builders have been walking past without seeing. That is where the Riemann hypothesis sits. The clue from the physics, the hidden instrument, is the field's best guess at where the door might be. But no one has found the door, and the ladders keep coming up one rung short. At the turn of this century, a mathematical institute named the Riemann Hypothesis, one of a small handful of problems carrying a $1 million prize for a solution. The prize has sat unclaimed the entire time, and anyone who has spent real time with the problem understands that the money was never the draw. The draw is that this single statement about where the zeros of one function fall sits underneath a vast portion of what we believe about the primes, and we cannot establish it, and we cannot say precisely why we cannot. We have a statement confirmed 10 trillion times without exception. We have a physical fingerprint suggesting it is the spectrum of some hidden instrument. We have 167 years of the finest minds unable to prove it, and a growing sense that proving it will require an idea nobody has had yet. All of that could read as a story of failure. But sit with what it actually shows, and it points somewhere else. A problem that resists this completely, for this long, against this much brilliance, is usually not just a hard puzzle. It is usually a sign that we are missing something fundamental about the objects involved, something that, once seen, would make the whole thing obvious in retrospect. The resistance is information. So perhaps the deepest question is no longer whether we can prove it, but what the difficulty itself has been trying to tell us all along. Strip away the zeta function, the complex plane, the zeros, all the machinery we spent this whole climb building, and ask what the Riemann hypothesis is actually a statement about. Underneath everything, it is a claim about how much order the whole numbers are permitted to contain, about whether the most basic objects in mathematics, the counting numbers you learned before you could read, hide a flaw at their foundation or hold together in perfect balance. That is the real subject. The zeros were only ever the place the question happened to become visible. If the hypothesis is true, the primes deviate from their expected count by exactly the square root amount, the amount an honest coin is entitled to, and no more. Their apparent chaos is disciplined chaos, disorder held to the tightest possible bound. If it is false, some hidden bias leans on the primes far out in the numbers, and their disorder exceeds what chance allows. One branch says the deepest layer of arithmetic is as balanced as anything can be. The other says a crack runs through it, invisible until you climb high enough to feel it tug. The entire 167-year effort has been an attempt to learn which world we live in. And here the primes force a genuinely uncomfortable idea about randomness itself. The primes are not random. Everyone is fixed by the rigid laws of multiplication, decided before any human counted them, carrying not a trace of chance. And yet, if Riemann was right, their large-scale scatter is statistically indistinguishable from the fairest coin ever flipped. They are perfectly determined and perfectly balanced at once. Which raises a question that reaches past number theory into everything. When we call anything random, are we describing the thing itself, or only the limits of what we have managed to decode? The primes look random exactly until you find the zeros, and then their disorder turns out to be the sound of a perfectly ordered set of waves. Perhaps randomness is never a property of the world. Perhaps it is always just order we have not yet learned to read. The spacing of the zeros match the energy levels of heavy atoms, systems no one would have thought to connect. But the pattern reaches further than that single coincidence. The statistics that describe the zeros show up in the resonances of vibrating plates, in the arrival times of buses that have fallen into step with one another, in the spectra of chaotic quantum systems of every description. Across all these unrelated settings, the same curve appears, the same repulsion, the same disciplined avoidance we first saw in the zeros. It is as if there is a universal shape that order takes when it disguises itself as chance, and the primes are simply one of the purest places it shows through. The Riemann hypothesis is a local instance of something that seems woven through the structure of mathematics itself. Now bring it all the way back down, out of the abstractions, to where you are counting. The primes are not distant curiosities. Every time a message travels securely across the internet, it leans on the difficulty of pulling large numbers apart into their primes. The atoms of arithmetic are running, right now, inside the device that carries these words, inside every bank transaction and every private message sent anywhere on Earth tonight. The question of whether those primes are perfectly balanced or secretly biased is not a question sealed off in a journal. It is a question about the behavior of the objects our entire digital world is quietly built on. We have staked a great deal on the primes being as orderly as we believe, and we still cannot prove they are. There is something almost vertiginous in that gap between how much we depend on the primes and how little we can prove about them. We have known they are infinite for over 2,000 years. We have known their average density for 200. We can compute them, encrypt with them, build the machinery of a civilization on them. And the single deepest fact about how they are arranged, whether they are balanced or flawed at the root, has stayed just out of reach the entire time, guarded by the position of points on a line no one can quite pin down. We built the modern world on objects whose fundamental character we have never been able to establish. The primes let us use them without ever letting us fully understand them. And whichever way the answer finally falls, something has already been settled by the asking. If the hypothesis is proven true, we will have learned that the foundation of counting is sound, balanced to the last possible degree, and we will likely have found the hidden instrument to prove it, opening a door between arithmetic and physics that no one can yet see through. If it is proven false, we will have learned that a bias hides in the integers themselves, and we will have to rebuild a great deal of what we thought we knew. Either outcome reshapes the landscape. But notice what the long failure to decide has already given us. In chasing this one line, we uncovered the connection between primes and quantum systems, between arithmetic and the physics of chaos, whole territories of mathematics that exist only because people could not stop asking why the zeros lie where they do. The question has been more generous unsolved than most questions are when answered. So we arrive, after all of it, at a strange and quiet place. The most balanced structure in mathematics may be sitting right in front of us, its perfect equilibrium confirmed 10 trillion times and provable not once. The primes hold their impossible poise, determined and yet balanced, ordered and yet wild, and they do it whether or not anyone ever writes down the reason. And the deepest example of that same poise, the same countless small forces balancing into something smooth and steady, is not out on the number line at all, or in a lump of uranium, or in the resonances of some abstract instrument. It is a great deal closer to you than that. Where, in all of this, does the balance finally touch the body of the person lying in the dark, listening? The same mathematics we followed all the way out to the zeros is running, at this moment, inside your chest. Not as a metaphor, as the same kind of equation, working at a different scale. The steady thing you feel when you rest a hand over your heart is built the exact way the smooth prime count is built, out of countless small irregular events that balance into something even. You have been carrying an instance of this all along. Consider what a heartbeat actually is underneath. It feels like a single clean pulse, one drumbeat, regular and whole, but it is nothing of the kind. Each beat is the sum of millions of individual cells, each one firing on its own slightly imperfect schedule, a little early here, a little late there, no single cell keeping perfect time. The smooth pulse you feel is not the behavior of any one of them. It is what emerges when all those small irregular firings are added together, the early ones and the late ones canceling against each other, the way the spinning arrows canceled, the way the waves from the zeros canceled everywhere except exactly where they should not. Out of a crowd of imperfect timekeepers, one steady beat. Your breathing is the same story told in air. The pressure you feel as you draw a slow breath in the dark seems continuous, a smooth filling and emptying. Beneath it, uncountable molecules are moving in complete disorder, striking the walls of your lungs at random, no two on the same path. There is no smoothness anywhere in that swarm. And yet the pressure is smooth, reliably, breath after breath, because the disorder of that many particles averages into something you can depend on. The chaos does not have to organize itself. It only has to be numerous, and randomness at that scale produces steadiness, as surely as it produced the fair coin balance of the primes. The calm of a single breath is the sound of an enormous number of small, chaotic things canceling into peace. We went looking for perfect balance at the outermost edge of mathematics, in the zeros of a function on a plane, in the energy levels of uranium, in a hidden instrument no one can find, and that same balance, order emerging from the sum of countless small disorders, turns out to be the thing keeping you alive as you lie here. The primes hold their poise because their waves balance. Your body holds its poise because its cells and molecules balance. It is the identical shape of order, disorder at the smallest scale, summing into steadiness at the scale you can feel. You do not have to travel to the number line to find the most balanced structure in mathematics. You are resting inside one. And there is a strange comfort in what stays true regardless of the proof. No one knows whether the zeros all lie on the line. Perhaps no one will for another 100 years. But the balance in your chest needs no proof to hold. The steadiness of your breath does not wait on anyone settling the hypothesis. The order was never something we had to establish for it to be real. It runs whether or not it is understood, in the primes and in the body alike, indifferent to whether anyone ever writes down why. The mathematics keeps the primes balanced tonight exactly as it keeps you balanced, and neither one is asking permission. So let the numbers rest now. The primes will still be infinite in the morning, still holding their impossible poise, still keeping the secret they have kept for 2,000 years. The zeros will still be climbing their line, 10 trillion of them confirmed and the rest waiting, patient, in no hurry to be found. None of it needs you awake to continue. The same steadiness you followed all the way out to the edge of what anyone knows is here, closer than the number line, closer than any equation, moving softly in and out with each breath you take in the dark. Thank you for spending this quiet stretch of the night with me, and for letting these ideas keep you company as you drift off. Rest well, sleep gently, and may the steady, balanced thing inside you carry you all the way through to morning.